In 2009, Western intelligence agencies uncovered information that dramatically reshaped strategic discussions in Washington and among U.S. allies near the holy Shiite city of Qom. Buried deep inside a mountain, Iran had secretly constructed a uranium enrichment site known as the Fordow Fuel Enrichment Plant. What made Fordow different was not simply its purpose, but its design philosophy. Unlike many nuclear facilities built in open terrain, Fordow was carved into solid rock. Its enrichment hulls were reportedly positioned 80 to 90 meters underground, shielded by layers of limestone, dolomite, and granite. Some geological assessments suggested that certain sections could be even deeper. This was not accidental engineering, it was intentional strategic planning. For Iranian planners, burial depth equaled survivability. The deeper the centrifuges were placed, the harder it would be for an adversary to destroy them using conventional weapons. The facility's location near Qom, one of the most important religious centers in Shiite Islam, added another dimension. Any strike near such a city would carry regional political consequences. In strategic terms, geography and symbolism were integrated into defense planning. By contrast, the larger enrichment complex at Natan's nuclear facility was more exposed and less deeply buried. While Natan's played a central role in Iran's enrichment activities, Fordow increasingly drew attention because of its fortification and reported enrichment levels. In 2023, inspectors from the International Atomic Energy Agency detected uranium particles enriched to 83.7% at Fordow, just below the 90% threshold typically associated with weapons-grade material. Although enrichment level alone does not equal weaponization, the proximity to that benchmark intensified international concern. For more than a decade, military analysts debated whether any conventional weapon could significantly damage a facility protected by so much rock. Destroying surface buildings is one thing. Neutralizing underground chambers protected by tens of meters of granite is another entirely. This challenge led to the development and refinement of specialized bunker-penetrating munitions, most notably the GBU-57 Massive Ordnance Penetrator. Unlike conventional bombs designed primarily for blast radius, the GBU-57 prioritizes penetration. Its structure consists largely of hardened steel, allowing it to survive extreme impact forces. The idea is simple but technically demanding. The weapon must remain intact long enough to burrow through earth, reinforced concrete, and rock before detonating at depth. Publicly available information indicates that the GBU-57 can penetrate substantial layers of soil and reinforced structures. Equipped with GPS and inertial navigation systems, it is designed for high-precision delivery. A programmable fuse allows detonation after reaching a calculated depth or upon detecting an internal void. However, such a weapon requires a compatible delivery platform. The Beta Spirit is widely known as the only operational aircraft capable of carrying this type of heavy penetrator into contested airspace. Its flying wing design minimizes radar reflection. By eliminating vertical tail surfaces and incorporating radar-absorbing materials, the B-2 achieves a significantly reduced radar signature compared to traditional bombers. The aircraft's engines are embedded within the fuselage to limit infrared visibility, and all weapons are carried internally. With intercontinental range and aerial refueling capability, the B-2 was designed for long-duration strategic missions. Only a limited number remain in service, making it both rare and strategically valuable. Iran's integrated air defense network reportedly includes systems such as the S-300, and some sources have speculated about elements related to the S-400. These systems are capable of engaging aircraft at long distances. For non-stealth platforms, penetrating such defenses would pose significant risk. In a complex strike scenario, stealth fighters like the F-35 Lightning II could play a supporting role by identifying radar emissions, mapping threat systems, and suppressing air defenses. Dedicated electronic warfare aircraft such as the A-18G Growler specialize in radar jamming and electromagnetic disruption, further complicating defensive tracking efforts. Reports have described a hypothetical or alleged coordinated operation referred to as Operation Midnight Hammer, according to those accounts. Multiple aircraft including stealth bombers, fighters, refueling tankers, and support platforms would operate in synchronized phases. Long-range flights, mid-air refueling, electronic warfare support, and precision-guided munitions would all be integrated into a tightly timed mission profile. Such an operation, if conducted, would represent years of planning. Deep underground targets require not only physical penetration capability but also precise intelligence mapping ventilation shafts, power systems, structural layouts, and geological composition. Military planning for hardened targets often involves simulation, modeling, and repeated assessment of penetration physics. Post-strike assessments in similar cases typically rely on satellite imagery, seismic readings, signals intelligence, and classified sources. Surface damage may appear minimal small entry points or craters, while the real effects occur deep underground. Even so, complete destruction of a hardened facility is extremely difficult to verify publicly. Damage assessments often use terms like degraded, disrupted, or delayed rather than eliminated. Strategically, the broader implication of such capabilities is significant. For decades, deeply buried facilities were considered among the most survivable military assets. Hardened bunkers, mountain complexes, and underground command centers were built under the assumption that depth provided near immunity from conventional attack. Advances in precision guidance, materials engineering, and penetration physics have challenged that assumption. At the same time, it is important to recognize that no system guarantees absolute success. Geological variability, structural reinforcement, redundancy in equipment, and rapid repair capabilities all influence outcomes. A strike might delay a program by months or years without permanently ending it. The story of Fordow illustrates a larger theme in modern military strategy: the continuous competition between protection and penetration. One side invests in deeper fortification. The other invests in stronger penetrators and stealth delivery systems. Technology evolves on both ends. Geography once offered a sense of permanence, mountains as shields, depth as security. Today, advances in engineering and targeting have complicated that logic. Yet physics remains neutral. Rock resists force. Steel converts kinetic energy into penetration. Explosives amplify internal pressure. The result depends on precise calculations, timing, and execution. Ultimately, the debate surrounding facilities like Fordow reflects the complexity of 21st-century security dynamics. Nuclear infrastructure, air defense systems, stealth aircraft, electronic warfare, and international inspections all intersect within a single strategic equation. There may be no absolutely invulnerable fortress, but neither is there an absolutely decisive weapon. Modern deterrence rests not only on capability, but on uncertainty. Uncertainty about effectiveness, escalation, retaliation, and long-term consequences. In that sense, the story is not only about a mountain facility in Iran. It is about the evolving balance between concealment and detection, between fortification and penetration, and between engineering ambition and geopolitical reality.